What's going on, everyone? Welcome back. And here's our sequence on mechanics of materials continued. And hopefully, you're coming from the overview on beam mechanics and some descriptions on the transformed area method for analyzing composite beams. And that's where we learned a little bit about the strain and stress profiles and how to transform the area so that we can analyze a composite beam. So in this video, I'm going to go through a very detailed example of a composite beam analysis. And in this example, there's going to be a simply supported beam that's made of two materials, wood and steel, whose moduli are shown there, 10 GPa for the wood and 200 GPa for the steel. There's going to be a distributed load uniform of 50 kilonewtons per meter, and the beam length will be 4 meters, and we can neglect the beam weight here. What we want to find is the maximum normal stress in the wood and the steel in the cross section. And the way we're going to do that, we're going to go through quite a few steps. And really, all these steps are part of flexural analysis, with the internal moment and calculating normal stresses due to that internal moment. So we're going to draw a shear moment diagram really fast. I'm not going to emphasize that too much because it's a simply supported beam. And then go into transforming the cross section into one material. And that's going to be the important part here. Then we'll calculate some geometric properties, which will be review, and then draw the normal stress profile of the transformed section, and then draw the normal strain and stress profile of the composite section. And the strain profile is really important. Is maybe not be emphasized enough in composite section analysis, but the strain profile is really important. It's the one thing that doesn't change in the transformed section analysis. The areas change, the stresses change in the transformed area analysis, but the strain profile is the one constant, and it's the one thing you can always hang your hat on, if you will. All right, so here is our drawing here. So the first thing to do is always obviously come up with a schematic. Here's the schematic here. I have a simply supported beam with a uniformly distributed load. I've got steel in the top layer, wood in the middle layer, steel in the bottom layer. And here's a view of my cross section of the beam. So if I were to make a slice and look into it, this is what I would see. And here are the dimensions that are given. And I've labeled this S, wood, and S for steel, W for wood, S for steel, just to show. And then I don't know if you can really see the brown too well, but it's there. And let's see. So the first thing we do is draw a shear moment diagram. And so in order to draw the shear moment diagram, we need reactions to the loading. And this is I know that I will have a horizontal reaction, a vertical reaction, and a vertical reaction here. I know that this, by some of the forces in the horizontal, is 0. I know that the resultant of this is 50 kilonewton per meter times 4 meters, which is going to be 200 kilonewtons. And because my loading and my boundary conditions are symmetric, loading and structure are symmetric, hey, guess what? Each of these, by equilibrium or whatever else you want to do it by, 100 kilonewtons each. Okay, and now I can draw the shear moment diagram. So here, let's see, got my straight edge. Bam. Bam. Okay. Got my straight edge, got my horizontal line for the shear function or shear diagram, got my horizontal axis for the moment diagram, the moment in kilonewton meters, and the shear in units of kilonewtons. And really, the story. If you not, go check it out or learn a video or ask your instructor, whatever, right? 100 kilonewtons to start, or some people say go up 100 kilonewtons right here. And then I decrease linearly at a rate of 50 kilonewtons per meter, or I have a slope of 50 kilonewtons per meter. And let's see, the middle is right about there. So I want to make sure I hit the middle correctly. And bam. Oh, right there. And that should be minus 100 kilonewtons right here. And this is my shear diagram. Bam. And this center, because again, my structure is symmetric, it would take me 2 meters to get down to here, or halfway. And then my moment diagram is, bam, because it starts at 0 here, I've got this area right here, 1/2 base times the height of that area, which is 1/2, boom, is 100 kilonewton meters. So here is parabolic because this is linear. So if this is constant, linear, parabolic function, right? And so here, and the slope here is 0 because my shear is 0. My slope here is a plus 100 because I have 100 here, the value. So I don't know if I drew that well. This is probably not the best drawing in the world, but nonetheless, it will suffice. And here, this max peak moment is 100 kilonewton meters. How nicely that location where we want to calculate our normal stresses is going to be here. This location right here at 2 meters, right in the midspan, because my maximum moment is going to be here. So that's where all my maximum normal stresses are going to occur. So based on the shear or the moment diagram, I can say M max is 100 kilonewton meters. And that's the moment I'm going to use. So now that I have a feel for what my maximum moment is, now I want to go next and look at the cross section and transform the cross section into one material. And in this case, I'm going to transform wood into an equivalent steel, okay, or into steel here. And you know, and I know that if you looked at the composites overview and the composites transformed area video, then you know that you can't change the height because that changes your strain profile and that just messes up your anchor, if you will, okay, or whatever your basis is for everything. But what you can change is the width because you need to change the area to satisfy force equilibrium or just have the same force. And so here, the relationship was that you take the modulus of elasticity or the modular ratio times the material dimension. So here, let's say this is a dimension of one material, and I want to convert it into material 2. So I have to take this dimension of material 1, multiply it by the modular ratio, and it gives me the equivalent in the other material. And for this problem here, we're going to convert wood into steel. So that would mean the modulus of elasticity of wood divided by the modulus of elasticity of steel and times the width of the wood that we want to convert is equal to an equivalent in steel. Okay, and I'm just going to call that BEQ right there. And so here, this was my steel, here was my wood, here was my steel. The height of this section, let's go back and look real fast, it was 350 and then 150 width. So here I had here like this, right here like that, and this was 50, 250 and 50 all in millimeters right here, and the width of this deal was 150. And really, the width of the wood that we have, the only wood is in the middle right here, in the core, I guess, like a sandwich beam, right? This was 150 millimeters. So this width of wood was 150 millimeters, and we're going to change that to an equivalent steel. So in this case here, this B equivalent, I'll go ahead and calculate it right here. This B equivalent, it was 10 GPa over, or it's going to be 10 GPa over 200 GPa times the width of the wood here, which is 150 millimeters, and punch that into my calculator, and that gives me 7.5 millimeters. So my transform section, here was my composite section, my transform section, all in one single material, now looks like this. So here I have this right here, like that, and then here it looks like an I-beam, really. So my steel stays the same dimension. Whatever steel I had before stays the same dimension, and then I have this I-beam with the really skinny middle right here. Here's my I-beam right here. And so all these dimensions, this dimension and this dimension, is still 50 millimeters. And this dimension and this right here is still 150 millimeters. Same here, this is still 50 millimeters. And this width right here is 7.5 millimeters right here. And the interior dimension right here is 250 millimeters. And this is my transformed section. And again, the key is the height did not change because we cannot alter the strain profile. So the only thing that we can modify of these areas are the width. Okay. Now what we want to do is really just calculate the geometric properties. And so here, the geometric properties of this, so this transformed section is all quote-unquote steel. And so here, let's make a note of that. All steel, right, converted into wood. I mean steel, all converted into steel. And the centroid, so we want to calculate some geometric properties. So let's see, 1, 2, 3, geometric properties of this transformed section. And really, we want to find where the neutral axis is. So the neutral axis is at the geometric centroid, so y bar in this case, because everything is symmetric, from the bottom here, it's going to be halfway, right? This whole cross section is symmetric. So this is, let's see, 250, it should be 175 millimeters from top or bottom, okay? So it's 175 millimeters. So our neutral axis, our centroid, is here. I'll do that in red, why not? Bam, like this, and this is the middle, and this distance right here is y bar equals 175 millimeters. And then the moment of inertia, the area moment of inertia, about the neutral axis, which is right here. Here is my, my neutral axis is right here. There's my neutral axis. This moment of inertia, I could use a parallel axis theorem, or I can also notice that, I could calculate the moment of inertia of this giant rectangle, 1/12 the base, which is 150 millimeters, times the height, which is 350 millimeters cubed, minus the holes, which would be kind of this region right here. This hole and this hole, which are the same dimensions. So there are two of those. And the reason I can just do the subtracting of the holes is because the geometry of this large rectangle, or sorry, the centroid of this large rectangle and the centroid of these holes are in the same point or same location. So I have this minus 1/12. The base of these two, I'd say times 2, because there's 2 of these holes. Minus, this is the minus sign continuing from over here. Minus 2 times 1/12 times the base of this, which is, let's see, 150 minus 7.5 divided by 2 is 71.25 millimeters, times the height of this hole is 250 millimeters cubed. And if I calculate all that out, I get the geometric or area moment of inertia is 3.504 times 10 to the 8th millimeters to the 4th. And I'm sure all of you are checking, because it's always nice to tell me I'm wrong. It's not that nice, but some people like to do it. It's all good. I'm okay with it either way. All right, so here I'll stop here for part 1 of the video, and then in part 2 we'll do the stresses at the top and bottom of the transform section, and then talk about how to get it back to the composite section. All right, see you in the next video. Bye.